Okay. Just a couple of things, just quickly on the announcements. You know about tutoring. They'd love to have you as a tutor, but if you do need help in any class, they have some tutors available. Bookstore hours, Mondays, Tuesdays, 8 to 6, Wednesdays, Thursdays, 8 to 5, and Fridays, 8 to 3, both campuses. The math team, not going to meet today, I know, and then maybe tomorrow. We'll see if we can manage to get that to happen tomorrow. And there may be a chance for Friday, but I don't know that either, so we'll see. And before we get, oh yeah, one other announcement. I think you know about it already. It's sort of that sad news that next week there's no classes. Yeah, so get over it. Okay. Yeah. Yeah, well, that's bad. You know, no calculus. Well, you'll be working on calculus, won't you? Yes, good.
I'm glad.
Yeah.
I'm running every day. I work Thursday to Sunday, and I have class Monday.
Wow.
I'm having free time now.
Wow.
And I work like 12 hours a day.
Wow.
Yeah.
That's tough. Where do you work?
I work at St. Vincent's State University.
At what?
St. Vincent's Hospital.
Oh. Yeah.
I work there.
Which hospital again?
St. Vincent's. St. Vincent's, like, it's next to UAB, like Birmingham.
Right.
St. Vincent's, do you know?
Okay. I'm not. Okay.
The St. Vincent's, like, babies born, like.
Oh.
It's like a main hospital for, like, delivery and stuff.
Okay. Is it part of UAB?
No.
No.
St. Vincent's is totally different, but it's close to UAB.
Is it? Okay.
It's
Okay.
a big hospital. Though.
Okay. Now, did you say St. Vincent's? Oh, I'm sorry. My hearing is so bad. Yes. That's real close to where we live, too. So, yeah, I drive by St. Vincent's every day, twice a day, going home, coming back. Yeah, good hospital, too. I've visited friends who've been in there. And at one time, I had a doctor who was based at that hospital. And so, yeah. All right, yeah. That keeps you busy, I know. Okay. So, I realized we didn't get to the last slide when we were wrapping up the problem that we were working on Monday. So I just wanted to show this slide. I don't know if you can tweak your mind back to what Monday's problem was like, but remember we had checked the error bound for M6 and T6, the square root of x, the integral of from 1 to 4 of square root of x dx. Okay, and I just failed to show. Oops, I'm sorry, I hadn't turned on the projector without no computer. And all right, I thought this was on. Here is the graph of that function that we were talking about, and we were, even though this was an integrable function, we were still doing the midpoint and the trapezoid rule for it, and estimating the area under that. Now, when you draw the graph of this, remember to do the error estimate, we used the second derivative, and we wanted the maximum value for that. Okay. Now this is the function, and this is a little misleading. No, it isn't. No, it isn't. This is exactly. This is not the function square root of x. That looks something quite different from this. But this is the second derivative of that, and the absolute value of it, and it was 1/4. And we did this in class. When you graph this, you see the maximum value for that would be right here, and that would be at 1/4. And that's why we chose that because for x equal 1, the maximum error the maximum second derivative would be here, not down here. Okay, that would be much less. So this is why we chose that. Now, so if you're ever uncertain and you have a graphing calculator, calculate your second derivative, plug it into the graphing calculator on the interval that you're interested in, find the maximum value, and that's what you use. They did that for you here. Didn't do that in class. But anyway, we had finished the problem, and we're about to start example 3. Any questions before we get going? Okay. Now this time, and this is almost more like real life, okay? What kind of area do you work at the hospital?
Food catering associate.
Did you say?
Catering associate. I'm just.
Oh, catering associate. Okay, right. Okay. I don't know if you had any interest in going into something like epidemiology or any other type of research like that. Quite often then, you take the problem differently. In other words, say you're doing a study and other studies have shown you can't get but certain accuracy on it. Well, then you say, in this study, we're trying to really tell if there's a difference. And what helps you get better precision in research and data is take more samples. Of course, more samples cost more money to take. So it's always a payoff there, the competition there, between how much can we spend, how much, Well, sometimes the question is, how many samples do we need to take before we can get to the accuracy we need? Okay? That's what this problem is doing. In this problem, it says find the N. Okay, let me get my pen back to black. Oh, and I forgot to mark roll. Let me get you down. Got you coming in. Where is my pen? Okay. This is disconcerting. There it is. Okay. Sorry about that. All right. Silva's here and Marcus is here. So I haven't seen Theo in quite a while. I hope he'll be coming soon. Okay. And let me just also do a commercial break here. In this class, only 3 students, of course, but I've received 0 papers, research papers. Please get those done. You do have, this is Thanksgiving holiday coming up. Lucky you get the whole week off. We have to work Monday, Tuesday, and Wednesday, but you get the whole week off, so take advantage of that. Get your papers done. Okay, the 2 of you have turned in your first test. Thank you very much. But I still think you got the second test still out, right? Okay, that'll be fine. Just encouraging you to do that. Now, I haven't given you the third test yet, have I? Okay, and that'll be, Today. I'm planning to, while we're saying that, let me make sure it got run off. I had it set aside to run off. Let me make sure it did get run off. I'm pretty sure it did. Because I'm pretty sure. There's test 2. Don't tell me there's only 1 copy. Yuck. Okay. I'm going to have to make another one. I don't know why. There's test 2. Oh, there it is. I got it. Yeah. Well, oh yeah. Okay. A couple copies didn't get staples in them. Okay, so that's why I was doing through them. So there's only 1, but I got some. So I will give you this before you leave today. Pick up your third test. Now at the top it says test 2, but it's really test 3. So I just did the test. Whoa! Did that suddenly get really? Or was it always out of focus? Hopefully that's a little easier to read. Okay. that said, let's go on to example 3. Page 434 in the new edition, wherever that is in the older edition section. The old edition 7.8, new edition 7.9, numerical integration. Example 3. So here what we're asked to do is find the n, how many iterations you need to make, how many partitions you need to make, such that colon sometimes means such that t sub n, the trapezoidal rule for that n, approximates this integral, the integral from 0 to 3, e to the minus x squared dx with an error at most 10 to the minus 4. E less than or equal to 10 to the minus 4. Okay? Now, and this is for the trapezoidal rule. So basically what we do here, if you go back to error for the trapezoidal rule, that's on page 433 or the previous page, wherever you find that. The error for the trapezoidal rule, Tn, I'm abbreviating greatly, is less than or equal to K2, remember what that was? Maximum value for your second derivative within the range that you're dealing with. B minus A, and what's your B minus A in this problem? 3. Yeah. 3 minus 0, cubed, B minus A cubed, divided by 12n squared. Okay? If it was a midpoint rule, it would have been 24n squared. Okay? Well, we already know what we want the e to be, 10 to the 4th, minus 4. So basically we have that 10 to the minus 4 needs to be less than or equal to, now the K2, what did we say that was? K2? Okay. Boy. There it is, yeah. K2 is a number such that the absolute value of the second derivative of the function is always less than or equal to K2. So what we're going to do is take the second derivative of the function. Here's the function. What's its first derivative? F prime is equal to what? E to the minus x squared. Second? Not yet. Chain rule, minus 2x. Right? Okay. So what about f double prime? Okay. We're going to have another chain rule, but we also have a product rule to deal with now. So how do we do that? Okay, if you start with negative 2x, then you do derivative of the second part, which we just did, and that was a negative 2x e to the minus x squared, right? Plus derivative of minus 2x, which is minus 2. So that's going to wind up being a minus, not a plus. Minus 2 e to the minus x squared. Okay? Now, we want the absolute value of the maximum of this between 0 and 3. So let me rewrite this a little bit. This has two minuses. That's a plus. Okay? So that would be 4x squared e to the minus x squared minus 2e to the minus x squared. I'm going to pull out the 2e to the minus x squared. And that's going to leave me 2x squared minus 1. Do you see that? Okay. Now, we want the absolute value of that. And this is a little puzzling, you might say, because when x is going from 0 to 1, okay, when x is 0, this thing is negative 1. Okay? So we would need to do the other one. And anything up to, let's see, x equals 1 over root 2, which I think is 0.707, then that would be 0 then, because 1 over root 2 squared would be 1 half, 1 half times 1 half, 1, 1 minus 1 is 0. So, between 0 and 1 over root 2, you have to reverse these, make the absolute value, and then beyond that. So, really, you need to do a plot of this like we did it before. That's what they've done here. Thank you very much. Okay? What they did here was draw the plot, and this is what I'm suggesting you do. If you have a graphing calculator, do this. Once you get that, what that value is, this is what we just said. Now, yeah. What I did, they just factored out the e to the minus x squared and left it 4x squared minus 2. It's the same answer we got. I just factored it a little differently, okay? And I guess they've got a reason for it. So this thing here, which is the same as this thing here, here's what it plots as, okay? From 0 to 3. From 0 here is at negative 2, okay? X is equal to 0. Then this thing is equal to negative 2 times e to the 0, so that would be minus 2. And then it's decreasing, actually increasing, but the absolute value is decreasing until you get here, it goes to 0 here, that's 1 over root 2, by the way, 0.707. And then it increases again here and then starts falling off here. So obviously the absolute value of this thing is very small near 3. Here it's still less than 1. Here the absolute value is 2. So the maximum absolute value is 2. So that's what we're going to use for our K2. K2 is 2. Do you see how we got that? Okay. So let me get out of here. Okay. So our K2 is 2 times 3 cubed is 27 divided by 12 times n squared. Okay? So basically all we have to do is solve for n. Okay? So n squared is equal to, I'm going to simplify this as much as I can. 2 will go into 12 6 times. 3 will go into 6 twice. 3 will go into 27 9 times. Okay? So what we have is 9 halves times 10 to the 4th. Because when you multiply both sides of the equation by 10 to the 4th, that goes, the left-hand side goes to 0, and you wind up with it on the right-hand side. So what that is 4. Okay. All right. If you divide by 10 to the minus 4, that's the same as multiplying by 10 to the positive 4. right? Okay, because this is 1 over 10,000. And if you multiply both sides by 10,000. Okay. So this comes up 4.5 times 10 to the 4th, which would be 450,000. Oops. Yuck. 450,000 n. Oh wait, that's the square root. I mean, that's the n squared. Take the square root of that to get n. And if someone would do that, the square root of, and basically, let me tell you what it would be. That would be 100, that 10, that would be 100. So it's square root of 45 times 100. Square root of 45 would be 3 times root 5. What would that be? Square root of 450,000, or, yeah, that'll be the easiest. Say again? 412? Huh? 212. Okay. 212. Okay. Maybe just for safety, you make it 213. But frankly, I think 212 would be fine. That's approximately 212. If you wanted a little more, do it 215. I don't care. I mean, yeah, anything beyond that makes it more precise. So if you wanted at least 10 to the minus 4, 213. Okay, that should work. Okay. If there was a decimal there, do it. All right, let's see if we can find that. Yeah, here we go. And that gave you 212.1. So I would say, what's that? Right. So I would just bump it up to 213. Okay. Because you want to make sure you're less than that amount, 10 to the minus 4. So throw an extra in there. The fraction generally is not going to hurt you, but it's going to be close enough. Okay. Now, that done, we're ready for another way to do this. Now, this is a different figure from the one that shows in your text. It's somewhat similar, but it's the same as yours, but a little different from yours and mine. Okay? Bless you. Okay. As we have seen, the midpoint rule uses trapezoids that are tangent to the curve to approximate the area under the curve. The trapezoid rule uses trapezoids with vertices on the curve to approximate the area. In both cases, the top edge of each trapezoid is a straight line segment. Okay? In Simpson's rule, we replace the line segments with parabolas. Okay? Allowing us to obtain a curve fitted to a curve, which usually is going to be a little bit better. Okay? Allowing us to obtain an approximation that's usually substantially more accurate. To begin with, we subdivide A to B, just like we did before, into n increments. That's just like we did before, subintervals. Each one has a length of delta x, which is b minus a over n. Sorry, is this just too cool in here, or you just got the sneezes? I know, I can't help it. I gripe and complain on this all the time. They used to have an old thermostat here that I could adjust. Now they put a new system in, and they make it absolutely, it's all controlled over in some building somewhere else. They have it set for 68, which is too cold to have it set, and so therefore the air blowing out of there is considerably less than 68, so I hate it. Sorry, can't do anything with it. When we have a meeting with them, I'm going to try to convince them that you need to have something greater than 68 degrees. Now, in the wintertime, when it's cold outside and everybody's really dressed warmly, 68 may be fine. But when it's nice weather, like in the 70s today, I'm dressed like this. You know, you probably have on lighter clothes too. It's just ridiculous to have it set at 68. I would be okay with 78, but some students get a little sleepy then. So 70, 72, 73, 75, I would be very happy with. All right, anyway. So as we're saying, we're going to subdivide the interval. Okay. Going to try to not write on the screen to get back to this. Okay. Your interval length, delta x, is still b minus a divided by n. Whatever your limits are divided by the n, that's going to be your delta x. However, in this case, we require n to be even. And there's a reason for that. In midpoint rule, trapezoid rule, you could have 5 intervals, you could have 15 intervals, you could have 25 intervals, you could have 100, you could have had 213 intervals. Okay, that's what that last problem produced. Okay, yeah, you can set it anything you want to. In Simpson's rule, you're going to have an even number. So if your answer came out, you needed 213, bump it up to 214, because you've got to have an even number of intervals. Okay. Sorry, I've got my nose is running too. Okay. Sorry. I hate to do this in class. I'm crazy. Blowing my nose in this nicer weather. Okay. Now, then we pair up the resulting intervals from x0 to x1, x1 to x2, x2 to x3, x3 to x4, and so on. For each pair of intervals, we find a parabola that passes through 3 points on the curve above the endpoints of the 2 intervals. Okay? And that's what... Okay. Sorry. Let me back off. In the trapezoid rule, we use, if we're trying to estimate the area under this curve, we would take, and we had 3 intervals, okay? We would take this endpoint, the trapezoid going to that point, to that point, to that point. That's the trapezoid, trapezoid, trapezoid. Using the midpoint rule, we do the midpoint there and do the trapezoid tangent to the midpoint, tangent to that midpoint, and tangent to that midpoint. And as we noted before, in a downward sloping curve like this, the trapezoid rule always underestimates, and it's not significant, but it's still a pretty decent sized error there, the white. Here, the midpoint for this one is going to overestimate just a little bit, a lot less than this underestimate. So, what I can almost hear you saying, why don't we combine the 2? Well, guess what? That's what Simpson's rule does. But it can't do it with 3 intervals. It's got to have 4. Okay? So you'd have to always do that. So if f of x is concave down, Tn is smaller, the trapezoid rule estimate is smaller, and the midpoint estimate is larger. Midpoint estimate's better, but the trapezoid rule is in the other direction. Okay. Now, okay, they jump just to the other thing. All right. Let me see if they have us. No. They don't show a slide like you have in the book. I wish they had one. That would be pretty nice. In the new edition, we have a curve like this, not quite like this, but close to it. And if you're estimating that with a parabola, you can do a whole lot better job, okay? Number one, that looks like it might be a parabola to begin with. You get exactly the right answer. But even if that wasn't, if that was part of a sine curve or a cosine curve or something, still a parabola is going to do a lot better fit than either midpoint, trapezoid, or midpoint width. Okay? And you see that in your text in the new edition. All right. Now they do a lot different presentation here than they do in that edition. Okay. The bottom line we get down to in fact, they never even mentioned this formula. I would thought they would have, because they based the whole thing in the former edition on this formula. So you'll see this, Marcus, you won't. This is what Simpson's rule comes out being. And it's a rather strange notation, but it does work. Okay? But this, to me, isn't the easiest way to go. Now, number one, if you remember, midpoint rule is more precise than the trapezoid rule. In fact, it's twice as good. So they give twice the weight to the midpoint and only half the weight of that to this one. So basically, they split it up into thirds. Okay? Okay. So what? On the one hand, Simpson's rule is taking 1/3 of the trapezoid rule and adding to that 2/3 of the midpoint rule. Okay? And remember those formulas. They were very different, but they had some similarities. Okay? Now, another thing to note here is whatever your n is here, give me an n. Okay, make up a number. Second? Okay, let's make it even. Huh? Okay, a little bit. How about 10? Okay, I'll do whatever I want to do. Okay, let's make it 10. It has to be even here. So that would be 1/3 the trapezoid rule for n equal 5 plus 2/3 the midpoint rule for n equal 5. Okay? So automatically, the Simpson's rule is going to have twice the interval, so that makes it more precise then, but it also gets a better combination of high and low and averages out a lot better. Okay. Now that's how the previous edition approached it. The current edition actually does areas under a parabola. Okay? And either way you do it, okay, now, I'm going to back up a little bit here. Remember, we had the intervals, okay? Now, this is for Simpson's rule, using the ones for midpoint and trapezoid rule. Your intervals now are 0, x of 0, x of 2, because you have twice as many of them for Simpson's rule as you do that. X of 2 to x of 4, x of 4, up to x of n minus 2 to x of n. You need 3 intervals of 3 divisions under each parabola, because you have 2 endpoints and something like the vertex in between. It won't be necessarily the vertex, some other point in between. Okay? So that's why you have twice as many intervals. Okay. Now, this is showing actually how you do this, and this, I think, may be example 4. Or maybe not. Let's see. Okay. I chose 10. They're choosing 8. If you do S of 8 using 8 subintervals, then the even endpoints are used for T sub 4 and the odd endpoints for M4. Okay? So S8 would be, again, this formula here, 1/3 of T4 plus 2/3 of M4. Okay? And even though these are smaller or larger subdivisions, when you combine them this way, you get something far more accurate than what you had before. Okay? And again, this is rather bizarre. This is showing 8 subintervals, but you're doing 2 at a time. So you're doing these two to calculate that one. For trapezoid rule, these two to calculate that one for the midpoint rule. So you just go down the line that way. And it's not completely obvious, I think, till we actually do a problem. But it's much easier than they're making this seem to be, or somewhat easier. Here's Simpson's rule. Now, this is the same in both texts. And this is what I wanted to get at, rather than waste a lot of time trying to justify or rationalize the two presentations. Let's just look at it. Remember, your n for Simpson's rule always has to be even. 10, 8, 16, whatever. 214. That would be fine. Okay. The nth approximation, remember n having to be even then, for an integral from a to b of f of x dx, especially if that f of x is not integrable. Okay? By Simpson's rule, then this is what you do. Now, if you remember, for midpoint rule, it's just a d delta x out here. For trapezoid rule, it's a half delta x. For Simpson's rule, it's a third delta x. Remember that third was in there everywhere. Okay? So it's a third delta x times. Now, if you remember for the trapezoid rule, you had 1 here, 2, 2, 2, 2, 2, 2, and 1. Okay? And for the midpoint rule, you just had each value. You didn't have any coefficients in there. But remember, you've done 2/3 the midpoint rule. So every midpoint thing has 2 entries. Every trapezoid one has 1 entry, but remember it had odd things. So here's what it turns out to. Y0 is counted once and only once. Y1 was counted twice in the trapezoid rule and once in the midpoint rule, but we're doing 2/3 times that, so that'd be twice there. So that's going to be 4. Okay? Y2 had 2 from the midpoint. It wasn't used in the trapezoid. 2 from the trapezoid rule. It wasn't used in the midpoint rule. So that's the 2. So here's what your coefficients are. The first one's 1. The last one's 1. And in between that is 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, until the next to the last one's a 4, and then a 1 again. Okay? So you have 1, 4, 2, 4, 2, 4, 2, 4, 2, 4, 2, 4, 1. Okay? That's how it pans out. Now, what's your delta x? Just like before, b minus a over n. And your y sub j, these various y's, are whatever your n was, okay? Then it's that gives you your delta x, and then you do a different y sub j for each delta x, okay? And again, a lot of blah, blah, blah. I think when we do an example, it's going to make more sense. So let's see if we can. In this book, it's in the Conceptual Insight, the new edition, that they talk about the 2/3 midpoint and 1/3 trapezoid. You get it whichever way you approach it, parabolas or midpoint rule, or the combinations. So this is the formula whichever way you get it. Okay, so let's do example 4. Use Simpson's rule with n equal 8. That's legitimate, isn't it? Even number. To approximate this integral from 2 to 4 of the square root of 1 plus x cubed dx. Is that the one in your book? Okay, good. All right. Now let me just tell you, try as you might, you're never going to find the integral for that. Okay? It's not going to be in the table. It's not going to be anywhere. The only way you can do that is numerically. And Simpson's rule is the most precise, easiest to get to a solution, the fastest. Okay? So what do we do? First thing they do your you split your interval from 2 to 4 into 8 pieces. So that's 4 minus 2 divided by 8. That would be 2 over 8, which is 1 over 4. That's your delta x. It's 1/4. Okay? So you're starting at 2. You have 2, 2 1/4, 2 1/2, 2 3/4, 3, 3 1/4, 3 1/2, 3 3/4, 4. Okay? There's your division. Okay? Next thing you do, identify your coefficients. And if you go back, remember the first coefficient is always 1, the last one's 1. And then in between that, they alternate between 4s and 2s, ending on a 4 right before you get back to 1. 4, 2, 4, 2, 4, 2, 4, and then 1. Okay? Every time. Okay? So, those are your coefficients. And what do you do next? Well, let's go back to Simpson's rule and see. You do the 1/3. I can do that. Delta x, we had 1/4, 0.25. Then your coefficients we had, and then you do evaluate that function at the first point, then at each of the other points, multiply it by the appropriate coefficient, and then at the end point. So basically, let's go back here, and what you would do would be, okay, Simpson's rule for 8 would be 1/3 of 1/4, because that was your delta x. Okay, and then these are your calculations. Okay, the square root of 1 plus 2 squared, 2 cubed. Well, 2 cubed is 8. 1 plus 8 is 9. So that would be square root of 9 is 3. So I can do that one in my head. Yuck, hit the wrong key. Okay, what is wrong with this picture? There we go. I couldn't get the... All right, try this again. Okay. So, x equal to, that answers 3, right? Okay. Then that's plus 4, that's your coefficient, times the square root of 1 plus 2.25 cubed. Right? Plus 2 times the square root of 1 plus 2.5 cubed. Right? So that's what you do down the line. Plus 4 times the square root of 1 plus 2.75 cubed. Okay? Plus 2 times the square root of 1 plus 3 cubed. Plus 4 times the square root of 1 plus 3.25 cubed. Plus 2 times the square root of 1 plus 3.5 cubed. Plus 4 times the square root of 1 plus 3.75 cubed. Plus the square root, coefficient 1 here, 1 plus 4 cubed. That's 4 cubed, I think it's 64. That'd be square root of 65. Okay. All right. Make sure you have 9 terms. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we got them all in there. So, knock yourself out. Okay? Get your calculator down. Thumb through this. Do what it's required. And at the end, you'll get an approximation to that function. Okay? Think what? Let's see, do they show the table here? They come up with something on the order of 10.7. Okay? I don't know if y'all have done it, but if you have, more power to you. Okay. Let's see if they show any more on here. No, that's a different problem. Okay. So, take it home, play with it. You know, you can play with it now if you want to. The main difference in Simpson's rule, keeping up with those coefficients. Again, you split your interval, you do all that, set it up, but write down those coefficients so you don't blow it. And remember, it's 1, 4, 2, 4, 2, 4, 2, 4, 2, ending with a 4 before the last one. Okay? That's what it is for everything, but you have to have an even number. Okay. Let's move on to example 5. Boy, my head is clogging up like crazy. There's cold air blowing on me. Okay. Now, example 5 is estimating integrals from numerical data. Okay. Reality check here. Okay. In real life, we've seen that a lot of functions are just not integral. Okay? So therefore, you have to use numerical integration. But in real life, quite often we don't even have the function. We just have a bunch of data points. Okay? And we don't have a function that is a best fit curve to that. Even if we did, that may be a really complicated function. Okay? And it probably wouldn't be integrable. So in reality, we usually just integrate using data points. And that's what they're suggesting here. Example 5, estimating integrals from numerical data. The velocity in kilometers per hour, of a Piper Cub aircraft traveling due west is recorded every minute during the first 10 minutes after takeoff. So its velocity is recorded every minute during the first 10 minutes after takeoff. It says use Simpson's rule to estimate the distance traveled. Okay? So we don't even have a function we can plug in. We just plug in the values that we have here. And here are those values. I think I'll blow this up just for you to see. But when I go to write on it, it's going to reduce. So this is the first 10 minutes of flight in a Piper Cub. These are your velocities. Of course, when you first start, it's at 0 velocity. You take off, and 1 minute later, you're at 80 kilometers per hour. 2 minutes later, 100, then 128, 124, 160. But at that point, we kind of level off. Okay? Sorry, I'm having trouble breathing. Okay. So up to time 5 minutes, they've been steadily increasing, but now they sort of even out, and it goes, let's back up to 3 minutes. 128, 144, 160, 152, 120, 136, 128, 120, 136. So it's kind of seems to be balancing up there somewhere around 120 to 130. Okay? But it could be that it just hit a lot of wind there. I don't know. Okay. But anyway, those are your data. It's what you got. It's what you got to play with. Now, do we try to find a function that fits those data? No, that's going to be miserable. Okay? We just try to integrate what we've got. Okay? Now, fortunately, we have an even number of n, 10. So that'll work for Simpson's rule. Okay? The next thing we do, and I'm going to have to shrink down now, is identify your coefficients. And what were they again? 1 for Simpson's rule. 4. And by the way, they don't ever mention who in the world Simpson was, I don't think. Okay? I don't remember seeing it anywhere in here. That would be a good paper topic. Now, there's no guy named trapezoid and none one named midpoint. Those are just descriptors. Simpson, though, was a person. So that's a potential paper topic. Who was he? How did he develop this? Yeah, whatever. Okay. Now, your coefficients are 1, 4. You keep me going. 2, 4, 2, 4, 2, 4, 2, 4, 1. Very good. 1's at the end. 4's right next to the 1's, and then alternating 2's and 4's everywhere else. And you see why no matter what even number it is, if it was only 8, then this would be the 1 and it's a 4 next to it. Chop off 2 and you're the one right next to this becomes a 1, and then it's always 4. So it works. Okay. So those are your coefficients. Okay. Now, use this to estimate the distance traveled. Well, let's see. Remind me what distance traveled is. Distance traveled is equal to velocity times time. If you're driving from here to Tuscaloosa, let's count that what? 70 miles? Is that about right? I don't know. Okay. And if you drive at 70 miles per hour, how long is it going to take you to get there? 1 hour. Okay. Well, distance is equal to velocity times time. 1 hour times, 70 miles per hour times 1 hour will give you 70 miles. Okay. If you drove same rate of speed 2 hours, you'd be 140. So that's what it is. So, all right, what we're trying to do is estimate the distance. So that could be expressed as the integral from a to b of v of t dt. Okay? If you think about that, that's your speed, the dt is your time. You're just doing little bitty increments of it. So that's how we're going to be approximating that. So the delta t here is what? 1 minute. Okay? So your delta t is 1 minute. So your Simpson's rule for 10 is going to be 1/3 of 1, that's your delta t, and then it's your velocities at each of those things. So it's 1 times 0 is 0, plus 4, huh? Okay. All right. Yeah. Here's what the problem with that is. These are in minutes, and that's in kilometers per hour. So, yeah. So your delta t is not 1, it's 1 over 60. It's 1/60th of an hour, because these velocities are in kilometers per hour. So, yeah, that's exactly right. Yeah, your delta t would be in 1/60th of an hour, which would be they're in minutes, which are 1/60th of an hour. That's what I was trying to say. So then you got 0 plus 4 times 80 is 320, plus 2 times 100 is 200, plus 4 times 128. I'm not going to figure that one in my head. Plus 2 times 144, which is 288, plus 4 times 160, which would be, I'm pretty sure that's 640. Is that right? Yeah, 640 plus 2 times 152, that's 304 plus 480, 4 times 120 plus 136. Okay. Okay. So that's what you do. You multiply this times that. Before, you calculated the V according to the formula. We don't have a formula. All we have are the numbers. Okay? The 1/3 Simpson's rule, your time interval, or 60th of an hour, it's a minute. That's the 60th of an hour because these velocities are given in kilometers per hour. So the delta T is 1/60th of an hour. And then you do that. And the coefficients, I multiply the ones I could easily, I left for you to multiply the ones I couldn't. I got all but one. So that's not too bad. Add them up and figure out what it is. They claim that it's about 21.2 kilometers. Okay. Okay, I'm trying to find goodness gracious. They show the figure here. I don't know if it's really helpful to me. This is the most helpful slide. But this is the figure that shows those data. The data points. Started at 0 and sped up, got its airspeed up, and then it actually slowed down a little bit. It's balancing out here. So basically, you're doing the area under there. But the velocities in kilometers per hour, these are in minutes, so therefore each of these is 1/60. Okay? And it's using Simpson's rule. I haven't drawn this yet, and I can't do a good job of it, but I'm going to do my best rendition of what these parabolas look like. Okay, I can't even get it to show up here. Okay. Goodness, it was easier when it was bigger. I can't see it now. Okay, my pen's not activated. Why not? There it is. All right, and this is just my best guess. There was a parabola. There's a parabola. There's a parabola. And you just keep doing like this. These are pretty ugly and sloppy looking parabolae. But you do that and you see what you have. You counted this one once. It was a midpoint here, so that's 2 times. And then it was a trapezoid, which is 2 times, so that gives you a 4 here. This one you only count twice. 4 twice here. So you just match your parabola as you go, and that's a pretty lousy drawing of them. But that's generally how you're lining this up. Okay. Now, remember what the error was for the trapezoid rule? It was K2, which was your maximum second derivative. Now we're K4, which is the maximum fourth derivative on that interval. So you have to have a function. Now, certainly the data things you can't do with this, but if you had a function, you got to have at least 4 derivatives on it. So if you got that 4th derivative, what its maximum value is. So, like I said before, calculate those derivatives, figure them out, get them into a formula, equation, and then plug that into a graphic calculator to see what your maximum is over that interval. Okay? So your fourth derivative now. And your b minus a is now raised to the fifth power, not the third power. For both trapezoid rule and midpoint rule, you use the third power. You use the second derivative, maximum second derivative, third power of the thing. This is fifth power. And then divide it by 180, okay? Remember before it was 12 or 24. Much big number here, which should write this down. And then before it was n squared, this is n to the fourth. You're dividing by a very large number raised to a very large power. So that's really going to make your error much less on this. Even though this could be a bigger number, and this certainly is a bigger number, but these two both reduce it significantly. Okay? So I think we're ready then for example 6. Okay? Let's see, I don't think we have a figure. That's from the old text. Okay? So let's do example 6. Calculate S8, Simpson's rule with 8 intervals, which is not very many, for this function, the integral from 1 to 3 of 1 over x dx. Now, what's special about this is we can actually calculate that one. This is a function we can integrate, okay? And we will do that, okay? But let's do Simpson's rule first, okay? Now, where would you begin? Okay, that is a certain thing we have to do, and we can do it now. The delta x is going to be what? 3 minus 1 over 8. And that would be 2 over 8. They seem to like 1/4 a lot, don't they? Okay, so there's your delta x. What next? Do your number line and start with 1 and go to 3. Split it into 8 intervals. 2 is going to be in the middle. Middle of that is 1.5. Middle of this is 2.5. And then do this as 1.25, 1.75, 2.25, and 2.75. Okay, or you could have just started at 1 and done a quarter, because you already did your delta x. But to me, that's pretty easy to do that way. Okay, you've got that done. Now what? Yeah, the coefficients, okay, and they are what? 1, 4, 2, 4, 4, 2, 4, and 1. Got it? Okay, and then the rest is history. Okay, it's pretty straightforward. Your Simpson's rule for 8 would then be 1/3, that's the coefficient for Simpson's rule, times 1/4, that's your delta x, times, and here's your sum. 1 over 1 is 1, multiplied by 1. Plus 4 over 1.25, right? Plus 2 over 1.5, plus 4 over 1.75, plus 2 over 2, I know what that is, 1, okay. Plus 4 over 2.5, plus 2 over, I got it wrong, that's 2.25. 2 over 2.5 plus 4 over 2.75 plus 1 over 3. Okay. Hopefully you have 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we do. Okay. It's not hard. It's tedious. It's a lot of punching on the computer, but it's not that hard to do. In fact, I would start this way. 1 plus 4 over 1.25 plus 2 over 1.5 plus 4 over 1.75 plus 1 plus 4 over 2.25 plus 2 over 2.5 plus 4 over 2.75 plus 1 over 3 equal divided by 12. Okay? That's what I would do. Not that bad of calculation. Just a lot of punching of buttons. Right? Now, if you've done that, at least the book did that, okay? And you notice they get about the same thing we did. That Simpson's rule comes out to be approximately 1.09. I'm just going to call that about 1.1, okay? I'm not sure we have enough precision to go any better than that, okay? So find the bound for the error in S8. So first they calculate S8. We did. Okay. Then it said find a bound for the error in S8. Well, I'm going to rewrite our function f of x rather than 1 over x and make it x to the minus 1. I just like doing derivatives with that better. So we need f prime of x, then would be what? Negative what? No, the derivative. Minus 1 times 1, that would be minus 1, x to the minus 2. Right? F double prime of x would then be 2 times x to the minus 3. Right? F triple prime of x is going to be minus 6, x to the minus 4, right? And f, the fourth derivative of f, okay, writing it like that, is 24, x to the minus 5th. You see that? Okay. Now, I know what, okay, sorry. I have a really good idea of what that function looks like, okay? It's going down pretty fast, right? 1 over x to the 5th. And it's between 1 and 3. You know what? I think I know where that's the maximum. At 1, okay? Because at 3, you have 1 over x, 3 to the 5th power. That's a very tiny little number. Whereas at 1, it's just 24. Okay, 1 over 1 to the 5th is, okay. So that k, our k4, is 24. You buy that? Okay. Now, what is our error? The error for Simpson's rule is you take the maximum. And that's going to happen at the left-hand endpoint because it's a decreasing function. Strictly decreasing. Right. I should be drawing it like this, okay? I'm drawing it for me, not for you. Okay. So that's going to be less than or equal to 24 times, and it's the b minus a, that would be 2 raised to the 5th power. Well, 2 to the 5th power, yes.
So then we took the 1 and we cut the 1 to the 2-fold x to the negative 5th power.
Okay. You're asking about the K4?
Yes.
Okay. K4 is the maximum value of your fourth derivative of this function in this interval. Okay? And the fourth derivative for the function everywhere is 24 times x to the minus 5th. Okay? So 24 over x to the 5th. Okay. Now, where is that its maximum value? On this interval. Okay? That would be 24 over 1 for this value. That's 24. And that would be 24 over 3 to the 5th power. Yeah, it is a very small number. That's a strictly decreasing function, so the maximum value is going to be on the left-hand end, right? And it's going to be 24, okay? So it's 24 times b minus a, 3 minus 1 is 2. 2 to the 5th power is? 32, isn't it? Okay, 32. So that will be 32. So you got some big numbers on top. So it doesn't look like a very good error bound, does it? Until you go to the denominator, that's 180, which is an even bigger number, times n to the 4th, that's 8 raised to the 4th power. Woohoo! You got some honkers on the bottom then. Okay, so let's see what we got. Oh boy, can we simplify this a little bit? What I'm going to do, I'm going to take 2 of these 8's away and make it 8 squared, and go 8 into 24 will be 3 times, and 8 into 32 will be 4 times. I just make my numbers small. Okay? I know that 3 will go into 18 60 times, 4 will go into 60 15 times. So what we have is 1 divided by 64 times 15. So 1 divided by 15, divide that by 64. What you get? Or you didn't have to do it that way. I just do it because we don't have a calculator. 0.001. 4, okay. That's pretty small, okay? You're to the nearest thousands in just 8. We didn't get kind of precision in trapezoid or midpoint rule. Now, this one we actually can do the calculation. Okay. Oh, no. Okay. We found a bound for the error that was something like 10 to the minus third. Now it says find the n so you can make your error at most 10 to the minus 6. Okay? So then we'll go up here and say 10 to the minus 6 is less than or equal to 24 times 32 divided by n to the 4th, I'm writing it out of order, times 180. Okay? So what I'm going to do is multiply both sides by n to the 4th. So we have n to the 4th is equal to 24 times 32 divided by 180 multiplied by 10 to the 6th. Okay? Well, that's going to give you a pretty good sized number. Okay, let's see if I can do anything to make it simpler, not a lot. So just do that. See what you get. Multiply 24 times 32, divide by 180, and then multiply that by 10 to the 6th. EFP 6. Okay, you got a number there? A huge number. This part's not too big, but that part's pretty large. Okay, got it? Okay. Now, take the 4th root of that. You know how to do that on your calculator? Take that number, and then you can raise it to the 1/4 power if you wanted to. Caret to the 1/4, or you could do a 4th root. Have those keys on most calculators too. However you do it, do it. Okay. Second. 0.45. Yeah. Yeah. So what I would do was make it 46. Why that? Two reasons. You always round up to get more precision, right? The second reason, you are using Simpson's rule, you need an even number. So 46 is what I'd use. That's what they got. Okay. Now, off to the side here, they say we can actually do that integration. So let's do it. That would be the integral. Let's do this as x to the minus 1. What is that? Antiderivative of x to the minus 1. No. This is a weird one because you would have x, You would have x to the 0 over 0, which you can't do. So then you stop and ask yourself, well, what function has a derivative of 1 over x? Log x, that's what it is. So that's ln of x at evaluation 1 to 3. So that'd be log 3 minus log 1. Anyone know what log 1 is? 0. Okay, so log 3. Someone tell me what log 3 is. ln 3. 1.099. Okay, and if you went back to your first thing, and I thought I wrote it down, but I can't see it now. When we did Simpson's rule that time, oh yeah, I rounded. Okay, the book had it as 1.09873. And you just told me log 3 was 1.09861. So guess what? They differ by 0.00012. We said the error is going to be about 0.001. We got it actually better than that, 0.00012. So that's why we use the maximum K4 that we had. That's not going to be it throughout. So yeah, we were already within 4 significant digits of the answer. Okay, with just S equal 8. And remember, we just calculated it and said, I wrote that down, but I didn't. It was 46 for Simpson's rule. Remember, to get 10 to the minus 4 accuracy in trapezoid rule, we were up in the neighborhood of, in that last problem, 213, remember? To get 10 to the minus 4. To get 10 to the minus 6, which is 2 more digits over, we only had to do 46. Okay? Simpson's rule is much, much faster. Okay. All right. Any comment on that? That was 7.9. The summary is here. And let's see. Okay. Remember those parabolic arcs? Okay. Now we get to see them on this. This is the old thing. The new edition started with the parabola. The old edition started with the combination of midpoint and thing. Now this is not going to quite fit nicely, but I'm going to get it as close as I can. Okay. I did all that and hit the wrong button. Okay, now, if you had just 3 points there, you had this endpoint, and the one in between. You do your best parabola to that. That's your dotted line here. Your actual curve's doing that. But you see, that's not a bad fit at all. You overshoot here, undershoot here. So on average, you're going to be pretty close. Okay? Now, what if, I'm guessing they took this out of this one here, or something pretty close to it. What if that's your function you're estimating? That's a mean-looking function. I'm not sure we can integrate it, but using Simpson's rule, and they have 6 subdivisions, so you can do it. The first parabola that's going to estimate these 3 points is this one. Man, that does a really good job there. The next one that estimates these, that's that one right there. That does a really fine job. And the next parabola that estimates those 3 is that one. So you see, you've got 3 really tight fits. That's what Simpson's rule does for you. Okay? It's much better than trapezoids. Whether they're trapezoidal rule or midpoint rule, it's so much better because it's fitting a curve to a curve, and you get a much, much better precision. It's actually a combination of the two, but in that combination, you even get even better. All right, good deal. Any questions? Okay. Now that was the last slide. Let's see if we can do our preliminary questions here. Do we have time? I don't know what time it is. Huh? It's 11, so we got 10 minutes. I think we can easily do these in 10 minutes. What are T1 and T2 for a function on 0 to 2 such that f of 0 is equal to 3, f of 1 is equal to 4, and f of 2 is equal to 3? Okay? Boy, that's more complicated than I thought it was going to be. T1, it's not hard. We're going to do T1, then we're going to do T2. Okay? And here's what we got. We got the interval from 0 to 2. So on the number line, you start at 0 and you go to 2. Huh? Okay. Now, f of 0 is equal to 3. F of 1 is equal to 4. And f of 2 is equal to 3. That's all we know. Okay? Now, if you're doing T1, you're just doing one interval from 0 to 2. That's all, folks. Okay? That's it. Okay? And then what's your approximation? For trapezoid rule, okay, if you go back one page, you'll see trapezoid rule listed there. The coefficient is 1/2 for trapezoid rule. Okay? Then you have your delta x. We're going to have to calculate that. And then you have y0, and in the trapezoid rule, the first and the last are always coefficients of 1, so that's just y1, it would be your y1 here, but it's, okay. For T1, this is y0 and this is y1. You only will have one interval, okay? So, what is your delta x? Your delta x for T1 is going to be b minus a, which is 2, over 1. That's going to be 2, okay? So you got 1/2 of 2 of 3 plus 3 is 6. Right? That's your values there. So these go out, so that's going to be 6. Think that's a really good estimation? Probably not. Okay, but we got it. Okay, let's do T2. Well, with T2, your delta x for T2 is going to be 2 divided by 2, which is 1. Okay, so that changes. So your T2 is still going to be 1/2, because that's the coefficient for trapezoid rule. But now your delta x is 1. And now you have 3 values here. Your y0 is still y0. But now you have a y1 here and a y2 there. Okay, sorry about that. And your coefficients are 1 2, 1. Okay, so plug those in. Your T2 is going to be 1/2 of 1 is 1/2 times Y0 is 3 plus 2 times 4 is 8 plus 3. Okay, so that's going to be 1/2 of, that looks like to me to be a 6 and 8 is 14. So that's going to be 7. So our T1 estimate was 6. Our T2 estimate was 7. I don't think either one of them are very good, but let's see what they got in the back. See how well they did. This is 7.9. Preliminary question. There it is. Yeah. T1 is 6, T2 is 7. They got it right. Good for them. You see how we got it? Okay? Oh, I couldn't find my questions there. Number 2. Let's erase all that. Any questions on that before I erase it? Okay. 2. For which graph in figure 15 will T sub n overestimate the integral, and how about M sub n? Okay, now I'm going to draw them one like this and one like this. Okay, for which one of those two graphs will your Tn overestimate the integral? The first or the second? Now the Tn, remember trapezoid rule, would take the endpoints wherever they are, and because that's curving downward, the trapezoid rule always underestimates. But on this one, and this is a pretty lousy graph, let me do it like this. Okay. Trapezoid rule would do this, this, and this. It's now overestimating. So the trapezoid rule overestimates the second one. Okay? The midpoint rule takes the tangent line, and since that's curving downward, that overestimates the first one and underestimates the second one. Neither as badly as the trapezoid rule did, but it's still reversed. So for which graph in figure 15 will T sub n overestimate the graph? That would be the graph of g of x. The second one was g of x. Let's see if that's what they say in the back. Oh, it doesn't give the answer in the back, but I'm pretty convinced that's it. Okay, number 3. How large is the error when the trapezoid rule is applied to a linear function? How large is the error when the trapezoid rule is applied to a linear function? It's what? Actually, it's 0. Why? Because, pick your interval here, whatever it is. The trapezoid here is there. The trapezoid there is there. It's right on the line. I mean, a linear function, the trapezoid rule is going to tell you exactly. As will the midpoint rule. It'll tell you exactly. Now, strangely enough, Simpson's rule doesn't do as well on a straight line. But guess what? Who needs an approximation on a straight line? You can always integrate a straight line. Forget about your thing. But it's going to be 0 for a straight line. And I hope I just explained it graphically. The trapezoid rule integrates linear functions exactly so the error will be 0. Okay, number 4. This answer is not in the back. What is the maximum maximum possible error if T4 is used to approximate this integral? Okay, I'm going to have to do some writing here, so let me erase all this stuff. Okay, how large will the error when the trapezoid rule is used to, no, I'm sorry. What is the maximum possible error if T4 is used to approximate this function, integral from 0 to 3 of f of x dx, where the absolute value, I'm sorry, I've been dealing with vectors in my other class and I wrote the vector magnitude, okay. Absolute value of f double prime, didn't they say, yeah, is less than or equal to 2 everywhere on that interval for all the x's on the interval. So what is the maximum possible error for that T4? How do we get that error for T4? Error for T4, remember what that one was? That was your K2, which is 2. That's the maximum error, maximum value for your second derivative, times b minus a to the third power, so that'd be 3 cubed. Let's go on and write this as 2, divided by 12 times n, which is 4 squared, wasn't it? Yeah, okay. So that would be 2 times 27 divided by 12 times 16. Okay? First thing I'm going to do is 2 into 12 will be 6. 3 will go into 27 9 times. So that would be 9 divided by 32. So someone figure out what that is. 9 divided by 32. Oh, the answer's not in the back there. So, say again? Okay. That sounds reasonable. They don't have the answers in the back. Number 5. What are the 2 graphical interpretations of the midpoint rule? 2 graphical interpretations of the midpoint rule. Well, we have a midpoint right here. Here's the first of these. It's the area under the thing at the midpoint, the rectangle at the midpoint. Or it's the trapezoid at the tangent at the midpoint. That's the same area because this part up here, I'm going to draw this one in red. That is exactly equal to, let's do this one in green, to this one here. So it's either the area under the rectangle that represents the midpoint, or it's the trapezoid at the tangent at the midpoint. And they come out being exactly the same. So that should be your number 5. Let's see if we can get there. The 2 graphical interpretation of midpoint rule are the sum of the areas of the midpoint rectangles and the sum of the areas of the tangential trapezoids. Exactly what we said, I think. Close. All right, homework exercises. Any of the odds 1 through 11? Any of the odds 13 through 21? Any of the odds either 23 or 25 or both? 27. Any of the odds 27 through 31. Any of either 33 or 35 or both. Either 37 or 39 or both. Now they say you need computer algebra system. I'm not sure you do, but see what you can do with that. Any of the odds 41 through 45. And you might need computer algebra system on some of those, if so, forget them. Either 47 or 49 or both. And any of the odds 51 through 55. Okay? And number 64 does talk about sometimes Simpson's rule performs poorly. And you can look at that if you want to. I was going to say something. That ends the chapter, and that has us ready for the test. I found them earlier and I buried them, so let me see if I can find them again. How are we doing on time? It's what? 11:10. Okay, well don't leave until I give you your test. I've got to find it first. I think this is it. Okay, I've got one stapled and one not stapled. Do y'all care?
Yeah, I have a staple. So.
Okay, you want the unstapled one? Okay, I think I've got these. Oh, wait. I gave you and none of you are going, neither of you will see Theo. Okay. Before you go, let me just quickly do this. Let me tell you which sections these are. I'm pretty sure, let me, I'll put that in place there. Let me go to, I think it would be easier to do from the table of contents. Okay, this is Chapter 7, Techniques of Integration. Okay. I'm pretty sure that 1 and 2 are both 7.1. 3 and 4 are 7.2. 5 and 6 are 7.3. 7 and 8 are 7.5. And 9 and 10 are numerical integration. 7.8 in your book, 7.9 in yours. Okay? All right, that pretty much wrapped it up. Y'all have a great Thanksgiving holiday.